This is our first class meeting, and we'll be looking at introduction to the course is an introduction to electrical and maintenance technology, and we'll be looking at the topics we'll be touching are fundamentals of electricity, introduction to residential wiring, commercial wiring, residential construction frames. We also touch about microcomputers, then principles and applied practices of residential wiring. So we now touch the advanced part of residential circuit installation, the circuit installation, and the rest of them, how to troubleshoot. Let's quickly start. We start with electricity. What's electricity? The basics. So when beginning to explore the world of electricity and electronics, it is vital to start by understanding the basics of voltage, current, and resistance. So these are the three basic building blocks. Required to manipulate and utilize electricity. At first, these concepts can be difficult to understand because there are things that we cannot see. You know, one cannot see the naked eye, the energy flowing through a wire, I'm sure you know, or the voltage of a battery sitting on the table. You know, even the lighting in the sky, you know, while visible, it is not truly the energy exchange happening from the cloud to the earth, but the reaction in the air, you know, to the energy passing through it. So in order to detect this energy transfer, we must use measurement tools. You know, tools like your multimeter, you know, your spectrum analyzer, your multimeter, your spectrum analyzer, you know, and your oscilloscopes. These are tools that we use to measure different parameters in electricity. You know, so let's see what is an electric charge. Electric charge. Electricity is the movement of electrons. You know, electrons move, you know, and the movement of these electrons create charge, you know, which we can harness to do different type of work. Example, your light bulb, you know, your stereo, your phones, you know, your television set, you know, are all harnessing the movement of the electrons in order to perform their basic functions. You know, they all operate using the same basic power source. You know, I mean the movement of electrons. So the three principles for this tutorial can be explained using electrons, or more specifically, the charge that they create. So your voltage is the difference in charge between 2 points. Your voltage or your potential difference is called the difference in charge between 2 points. Your current also is the rate at which your charge is flowing through a conducting material, and your resistance is a material tendency to resist the flow of charge. So when we talk about these values, we are really describing the movement of charge and thus the behavior of electrons. A circuit is a closed loop that allows charge to move from one place to another. A circuit is a closed loop on both ends that allows charge to flow from one end to the other. So components in the circuit allows us to control this charge and use it to perform work. Who is George Ohm? George Ohm, the popular George Ohm is a Bavarian scientist who studied electricity. Ohm started by describing a unit of resistance that is defined by current and voltage. So let us see what a voltage is. We define voltage as the amount of potential energy between 2 points on a circuit. The voltage can be defined as the amount of potential energy between 2 points in a circuit. So one point has more charge than the other. This difference in charge between the 2 points is called voltage, and it is measured in what? In volts. In volts, which technically the potential energy or difference between 2 points that will impart 1 joule of energy per coulomb charge that passes through it. So the unit of voltage is what? Volt. So when describing voltage, current, and resistance, a common analogy that we use is a water tank. A water tank. In this analogy, a charge is represented by the water amount. This is the pictorial and illustration of what we're talking about. A charge is represented by the water amount. Voltage is represented by the water pressure. And the current is represented by the water flow. So remember, your water is a charge, the pressure is the voltage, and the flow is the current. So consider a water tank at a certain height above the ground. At the bottom of this tank, there is a hose. So the pressure at the end of the hose can represent the voltage. The water in the tank represents the charge that the water contained in the charge, and the pressure at the bottom of the tank represents the voltage. So the more the water in the charge, the water in the tank rather, the higher the charge. That means the water which represents the charge, the more it is in the tank, the higher the charge. That means the more the pressure and correspondingly the more pressure measured at the end of the hose. That means if you keep adding more water, meaning if there is more charge, the higher the pressure at that means the voltage at the end of the tank. So you can think of this tank as a battery. A battery where we store a certain amount of energy and then release it. If we drain out our tank at a certain amount, the pressure created at the end of the hose goes down. That means if you reduce the amount of water in that tank, the pressure at the end of your hose coming out will reduce. I'm sure you know it is just a basic analogy of what goes on in your battery and how electricity works. So we can think of this as decreasing voltage. That means the more the amount of charge in your tank is directly proportional to the pressure that you release in your hose. You understand? That means the higher the charge, the higher the voltage. For example, your battery, as the amount of energy decreases, let's say your touch light, like the one I have here, as the amount of energy drains out in the battery, the light becomes dimmer. That means the pressure becomes lower in your tank, using the tank and water as the analogy. So what I want to say in reference is the lower the amount of charge in your battery, the lower the voltage. You understand? That's exactly what we are talking about. So let's talk about your current. the current. We can think, we are still using our water tank as an analogy. So we can think of the amount of water flowing through the hose, from the tank as the current. That means the amount of water flowing through the hose of the tank as the current. The higher the pressure of that water, the higher the flow, and vice versa. That means the lower the pressure coming out from the tank, the lower the pressure from the hose. So with water, we would measure the volume of the water flowing through the hose over a certain period of time. With electricity, we measure the amount of charge flowing through the circuit over a period of time. That means current is measured in amperes. Amperes, that is represented as amps. An ampere is defined as 6.24 raised to the power 10 by 18 electrons. That means it represents 1 coulomb of charge per second passing through a point in a circuit. Amps are represented in the equation by the letter I. Voltage by letter V. So let's now say that we have two tanks represented here. We have two tanks, each with a hose coming out from the bottom. Each tank has the exact same amount of water. These two tanks, let's say the amount of water is, let's say, 100 liters or 200 liters, depending on the amount of water we are using as our analogy. So the hose at the base of each tank, one is wider than the other. That means one is narrower than the other. So we measure the same amount of pressure at the end of each hose. But when the water begins to flow, the flow rate at the water in the tank with a narrower hose will be lesser than the flow rate of the water in the tank with the one with the wider hose. You understand? So in electrical terms, the current through a narrower hose is less than the current through a wider hose. So if you want the flow to be the same through both hoses, we have to increase the amount of charge, or we increase the width of the hose. So this increases the pressure, that means the voltage at the end of the narrow hose, pushing more water through the tank. This is analogous to an increase in voltage that causes an increase in current. That means the more the pressure, the more the voltage, the more the current. The more the voltage, the more the current. An increase in voltage causes an increase in current. An increase in voltage causes an increase in current. So we have seen the relationship between voltage and current. In all what we have been saying, that means the higher the amount of your voltage passing through a circuit, the amount of current also passing through, the amount of current passing through a circuit, also is directly proportional to the potential difference. That is the amount of voltage pass, on, and the amount of energy dissipated. So we are, and that is the relationship between voltage and current. So let's look at our resistance. That means the third parameter, which is resistance. So we are still looking at our water tanks, one with a narrow pipe and one with a wider pipe. You understand? So it stands to reason that we can't fit as much volume through a narrow pipe than a wider one at the same pressure. You understand? That means we can't fit as much volume through a narrow pipe, than we can fit through a wider pipe. It is just basic common sense. And that is resistance, because the narrower the pipe, the more the resistance. But the wider the pipe, the lesser the resistance. That means the narrow pipe resists the flow of water through it, even though the water is at the same pressure as the tank with the wider pipe. You understand? Low resistance, let's look at this pictorial analogy of what we are talking about. Low resistance, give from pardon me, a wider pipe gives low resistance, but a narrow pipe of the same pressure for both gives a higher resistance. So relating this in electrical terms will mean that by two circuits with equal voltage and different resistance, the circuit with the higher resistance will allow less charge to flow, meaning the circuit with higher resistance has less circuit flowing through it. So we bring us back to George Ohm, which defines the unit of resistance of 1 ohm as the resistance between 2 points in a conductor where the application of 1 volt will push 1 ampere or 1 coulomb of charge. This value is usually represented in schematics with the Greek letter ohm. This is the symbol for resistance. It is represented as ohm. This is the symbol omega or ohm. So we call them omega. So what is Ohm's law? Let's see what is Ohm's law. Representing, putting mathematical terms, relation between voltage, current, and resistance. So combining the element of voltage, current, and resistance, Ohm developed a formula which says voltage equals current multiplied by resistance. Voltage, in volts equals current in ampere multiplied by resistance in ohms. This is called the Ohm's law. Let's say that we have a circuit with a potential of 1 volt, that means a volt of 1 volt, and a current of 1 ampere and resistance of 1 ohm. Using the relationship, of Ohm's law, which is V equals IR, one unit of volt equals 1 ampere, plus 1. Let's say that this represents our tank with the wide hose. The amount of water in the tank is defined as 1 volt, and the narrowness, which is the resistance to flow of the hose, is defined as 1 ohm. Using Ohm's law, this gives us a flow of what? Of 1 ampere. So let us now, look at another analogy. Let's look at the tank with the narrow hose, because the hose is narrower. Its resistance to flow is higher, like I said initially. So let's define this resistance to be, let's say, 2 ohms, because it is now higher because the hose is narrower. So the amount of water in the tank using our Ohm's law will now be, let's say, of one unit volt equals, this is what we want to determine. We don't know what is this, multiplied by 2 ohms. So our ampere will now be mathematically saying that 0.5 of this, or if you know how to do your math, this looks a bit confusing. Let's say x equals 1, 2x equals 1 equals 1. So the x will be 1 over 2. So let's say it will now be 1 volt will be 0.5 ampere. That means half, of the current passing through it will now be lesser compared to when the resistance was just 1 ohms. So let's look at Ohm's law experiment. For this experiment, you want to use a 9-volt battery, to power an LED. That means a light emitting diode. LEDs are fragile and can, have only a certain amount of current flowing through them before they burn out. And so you are seeing a diode. I think I have a picture of it. Okay, this is it. This is a picture of a light emitting diode. So we now said we want to use a 9-volt battery to power an LED. So I will say that LEDs are fragile, and once it exceeds the normal amount of current that should pass through it, it destroys the LED. So in the combination of an LED, there will always be a current rating. There's always most of the current rating, for that LED, to not to burn out. You understand? So this is the maximum amount of current that can flow through in that particular LED before it burns out. So in this experiment, what the materials we require is, a multimeter, to measure the amount of current flowing through, a circuit, a 9-volt battery, a 560 ohm resistor, and an LEDs. So LEDs are what's known as a non-ohmic device. This means that the equation for the current flowing through the LED itself is not as simple as V equals IR. The LED introduces something called a voltage drop into the circuit, thus changing the amount of current running through it, because an LED, draws current, so it causes a voltage drop running through that circuit. However, in this experiment, you are simply trying to just protect the LED from overcurrent and from being destroyed, to determine the amount of current flowing. So we will neglect the current characteristics of the LED and choose the resistor value using the Ohm's law in order to be sure that the current through the LED is safe under 20 mega ampere. So for example, we have a 9-volt battery and the red LED or any other color, depending on which one you want, with a current rating of 20 milliamp or 0.20 amp. So to be safe, we'd rather not drive the LED at its maximum. So we don't want to the maximum, we don't want to reach the maximum, so it won't destroy it. So we work at a lower rating. So whatever I suggested current which is listed in its data sheet is 18 milliampere or 0.018 ampere. So if you simply connect the LED directly to the battery, the values of ohms will look like this. V equals IR. That means I equals, that's the current, because mathematically V equals R. And since we have no resistance yet, current equals to 9 volts over 9 equals over 0. Dividing 9 by 0 gives an infinite current. Well, there's nothing like infinity in normal sense in electricity, but as much current as the battery can deliver. Since we do not want the current flowing through our LED to go beyond our normal rating, we are going to need a resistor to help us resist the amount of current to our required rating. So this is just a circuit diagram of what we are talking about. So let's say we now want to use a 500 ohm resistance. So we to keep our current under a value that it will not destroy the the LED. So what we get in essence, determine what amount of resistance we need, for the current flowing through that circuit not to exceed the normal current rating that will destroy that LED. From mathematically, from that 9-volt battery and the current rating of 18 ampere, we need a resistance of 500 ohms, solving mathematically from Ohm's law. So this is just a pictorial view of what we are talking about. This is your battery connected to your LED source, your what do they call it? Your resistance, your resistor is here, and this is your complete circuit. So this current limiting resistor example is a common occurrence in your normal electronics. So you often need to use Ohm's law to change the amount of current flowing through the circuit. Another example is seen in this LilyPad LED board. So let's look at current limiting before or after the LED? Current limiting, before or after the LED? When do we need current limiting? Is it before or after the light emitting diode? To make things a little more complicated, you can place the current limiting resistor on either side of the LED and it will work just the same. It can be on the right side of the LED or on the left side of the LED. Anywhere you put the resistor, it works just fine. So now going further, we'll be looking at, we'll just quickly look at our next topic. Our next topic for this class. Pardon me, let me quickly bring up the material. Talking about residential wiring. Talking about your residential wiring. So we have looked at the basics of electricity. The basics of electricity. So now we want to now start talking about what exactly is residential wiring. Residential wiring. The basics of residential wiring. Introduction to how you electrically wire your do the wiring in your homes. Just the basics, the things you need to know. There are things that we can do on our own if you understand what we need to do. You understand what we need to do. It is not so complicated. There are things that we can embark upon by ourselves, but we need to be very, very careful because to avoid electrical shock, which can be very fatal. We need to understand what exactly we are doing. So welcome to the series includes residential electrical wiring. It touches residential plumbing, 3D design, construction of modeling when it comes to electrical wiring. So it is difficult to imagine a world without light. Like, just imagine a world without your lights, your bulbs, your fridge, your TV, your computer stereos, and that was how it was from a few hundred years ago when these things have not been invented. When electricity was originally used for practical purposes, it was used for communication in the form of electric telegraph and telephone. So petroleum and paraffin lamps were still lighting homes there. There was nothing like bulbs. What they were using then were, paraffin lamps in the early 1800s. So it was then that Thomas Edison, developed the lightning bulb. Thomas Edison, they call him the father of light. He was the one that developed the lightning bulb. Edison was responsible for the first central power station, and many power companies still bear his name. So if you compare today's power requirements to what was needed 100 years ago, you will be very shocked as to how things have developed from how it was some 100 years back. Today, power plants located all over the country generate electricity with huge turbine generators that are driven mostly by fossil fuels, nuclear energy, or hydropower. These turbines are driven by some by fossil fuels, some by nuclear reactors, even by hydropowers. So there are many factors that contribute to our growing demand for electricity. But for now, let's go back to residential wiring. Residential wiring. So, understanding residential electricity. Let's look at residential electricity. I'm sure you know there are residential electricity and there is commercial, even industrial, and their mode of wiring is practically different from each other. So we are looking now at residential electricity. You know, electrical systems can seem like a very confusing mess of wire. You know, electrical system can seem like, when you see all those complicated systems and you look at them, you'll be like, so what are these? You know, in your junction boards, in your cubicles, you know, around your homes, you know. So, but if you use common sense, like I said initially, and take necessary precautions, you can easily and safely handle most home wiring projects. Like I said, if you use your common sense and take necessary precautions, you can easily handle most wiring projects. Working with electrical wiring can be very, very intimidating. You know, can be intimidating, and that is if you have seen somebody, you know, being being uh, 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 being knocked off by uh, um, uh, uh, electric shock, then you will know that it is a very, very dangerous thing to embark upon. But the truth is, those that do it, you know, you know, are just very careful. Though you cannot just, if you are probably an electrical technician, they know that you know, one or two ways you have not, you know, felt shock. But the point is, if you are very careful, you will you know, guide yourself against most of this crazy electrical shock. You know, so let's see what are AC, alternating current. Alternating current changes constantly, you know, from 0 volts to 120 volts and back to 0 volts. That's how an alternative current works. This cycle repeats itself 60 times every second. In terms of your electric service, this is referred to as 120 volt ampere cycles by 60 hertz. 120 volt AC by 60 hertz. So the flow of electricity through a wire is comparable to the flow of water through a pipe, like I, you know, explained initially. So, however, in order for electrical current to flow, a return path must be provided, just as unpressurized water is drained from a house. Current must flow back through a neutral wire, which carries no voltage, So just as a pipe with a large diameter can carry a great volume of water than a narrow pipe, a large wire can also carry more current than a small wire. That means the amount of current flowing in a circuit is called amp or amperage or ampere, depending on, you know, what you want to call it. So most household circuits have a capacity of, let's say, 50 to 20 amp. Watt or wattage is a measurement of how much electrical power a device consumes. Watt or wattage is a measurement of how much electrical power a device consumes. It is the rate at which current is converted into other forms of energy, such as light, heat, or motion. You understand? Watt, it is the amount, let's say the watt rating of probably your microwave or your TV. They are different. It is the amount of electrical power your device consumes. That is why most of probably when you put your generator and you mistakenly probably put on your electrical iron, you realize that there is a change in operation in your electrical generator, because the amount of power, of electrical power, your electrical iron pulls out is higher than your normal, let's say probably your lamp or your television set, or probably your transistor radio. So, like I said, watt or wattage is a measurement of how much electrical power a device consumes. So, electricity travels at the rate that is close to the speed of light. No one has ever seen a volt. I don't think anyone has seen, a volt or an amp. But when these forces interact, you can see their effect in the things around us. Like I explained initially, the relationship between volt, amp, and current. The following equation may be used to determine the relationship between your volt, your amp, and the current means your volt multiplied by your current equals watt. That means your power is what? Your volt multiplied by your current. For example, if a device operates, let's say on a 120 volts and draws 3 amps of current, the following equation is used to determine how much power is consumed. How much power is consumed? Just multiply, your voltage by your current and give us 360 watts. So if you like to determine the amount of power needed for a device to operate, you simply, rearrange the equation. Let's say you now want to, the amount of power the device consumes and the voltage passing through it. You now want to know the normal amount of current, passing through that device. You can just rearrange your equation, when you know that your volt multiplied by ampere, your volt multiplied by your current gives you your power. If you now want to get your current, just divide your voltage, by both divide V from both sides, and your ampere, you get your current rating. So, for example, let's say if a 120 volt microwave uses an 850 watts of power, we can use the equation to get, our current. That means you just divide your power by your voltage. So the term amp and volt are named after two scientists who discovered them. The first person is Andre Marie Amp, who was a French physicist who determined how to measure the amount of current in a circuit. And the next person is Alessandro Volta, who is an Italian physicist who devised the first electric battery. So let's look at basic home electrical system. I want to see the basic home electrical system. The electrical power we use in generate is generated by power plants. I'm sure we know. Okay, for some of us that don't know, these are pictures of, picture of what the power plant is. Power is sent to a power grid, starting with a substation. I repeat, power is sent to a power grid from the base station, which is now sent to a transformer, which steps down, steps up or steps down, to a rating where it is acceptable, residentially. You understand? So high voltage transmission lines are used to send the power to cities and towns that may be hundreds of miles, like all these transmission lines.